let's talk about linear regression. So now we're at the part in the course where we've covered a lot of the fundamentals that we need to talk about some really interesting problems and sophisticated methods to deal with them. So we've done probability theory, we've done the basic theory of statistics, what it is to guess a number that we don't know anything about really, and quantify our uncertainty in that guess. And we formalized what it is that we mean by causality and the kinds of assumptions that we need in order to say anything about causal quantities when we can really only observe the data that we have in the real world. So now we're going to kind of put some of that stuff together, particularly the causality and statistics part, to talk about a tool, a general set of tools called regression, and in particular linear regression, which is really the starting point for any other kind of a regression type estimator. So what is regression? The basic idea is that you use data to guess a conditional mean function. So if you recall from our lectures about expectation and probability distributions, here what I'm showing is a kind of heat map of the joint density of two random variables, x and y. And what I've plotted in pink here is the conditional expectation of y given x. So at each value of x, we have a whole distribution for y. So you can kind of see what that looks like. If you were to draw, let's say I'll draw in green here. So here, the probability of y is low, and then it kind of maybe goes up like this, and then like that. Here, it's a lot more peaked. So this like dark black area, right, is the area of high probability for y at each value of x. So you can think of this as like, okay, if I take people with values of x between this and this, and I make a histogram of their y values, it'll look like that. But for people who have x values like between here and here, if I make a histogram, it'll look like this. So those are different for each stratum of the population defined in terms of x. And what we're plotting in the pink here is the conditional expectation of y given x. So for each of these histograms or densities, I find the mean, the population mean, and then I connect the dots, right? So I can do this for each substratum of the population in x. I find the value of the expected value of y, and then I connect the dots, and that's just to briefly review the concept of a conditional expectation here. Okay. So when we do regression, the idea is that we don't actually get to observe this joint density, and we don't get to directly observe the conditional expectation. All we get to see are our data. So what we have is a data set, which you can think of as a table with x and y columns, and we can plot that as a scatter plot. And the scatter plot will look like this. And what we're trying to do is we're trying to guess, okay, if we had actually this kind of heat map, the value of this, what is this shape here, this pink function? But all we have are these dots. And so it's kind of an exercise in curve fitting, if you're familiar with that, where you kind of try to draw a line through some points. Say, what is the line that best fits these data? But now that we understand a bit about probability, we know kind of what we mean. What we're actually trying to get at is what's the conditional expectation of y given x for the density, the joint density that these data are drawn from. That's really the question. So that's what regression is. That is the whole idea. How do we use the data to get at some curve like this, some function that is an estimate? So here we use the hat to show that this is a guess for the conditional expectation function. How do we get a guess for the conditional expectation function? And why should we care? Why does it matter that we know or don't know the conditional expectation function? Well, there's a couple of reasons, and they're all different. So the first is just pure description. So we might be interested in knowing, is there some kind of pattern between x and y? Vaguely, what's the shape of that relationship? So, like, for example, for what values of x do I expect y to be high? That's a fair thing to want to know about. There's also prediction. So if I see a new value of x, can I predict y before I see it? So let's say I gather some new data. Let's say these data points represent like somebody's blood pressure is the x value, and then the y value is their blood pressure in 3 years. Or maybe it's the presence or absence of some disease in the future. Okay. Say then somebody comes in to the clinic right now, and I measure their blood pressure. Let's say it's here, right? And I don't have the y value because that's not something I've measured. That's something I'm going to measure potentially in 2 or 3 years. But if I have this conditional expectation function, I can tell you what I expect their blood pressure to be in 2 or 3 years based on what it is today. And the way I would do that is I would take this value up here, and whatever this y value is, this is the best prediction I can do, right? I can say for people who have blood pressure, let's say this is equal to 130, right? When they're 45 years old, on average, those people will have blood pressure equal to, let's say, 140 when they are 50 years old. So that's the idea. You can use it for prediction. And you're probably familiar with this. There's tons of prediction algorithms now, both in medicine and outside of medicine. There's tons of things that you might want to know ahead of time before they happen, potentially so you can intervene, or for many other reasons. And we'll talk more about that a little bit later in the course, perhaps. And the last thing is for causality. So here I've called this variable x, but you can have regressions that have multiple variables. And we already saw in the last lecture that if we're trying to figure out what is the expected value of some potential outcome of what would have happened if I had treated everyone with treatment little a, I can get at that by finding the conditional expectation here. Mu is the conditional expectation of y given x equals x, and a is set to little a, and then forcing a to little a in that conditional expectation function. And so if I want to approximate that, I can approximate the expectation with a sample average, and all I need to do is guess what this function is. So here, this is a regression of our outcome y onto the covariates and some exposure a. And so we'll talk much more about how we can use regression models. Once we have a regression model, we can use them to estimate this quantity here, and therefore estimate causal effects, like causal risk ratios or causal risk differences, by using this kind of a plug-in estimator. The key thing to note is that these different use cases for regression, these are different uses of the same tools. And since they are different use cases, they actually require different approaches. So even though they're all using the same regression model, people often see, oh, okay, I always need to interpret this coefficient this way, or I always need to do this kind of test, or I always need to do whatever. And it's actually a lot more contextual and subtle than that, because it really depends on what your question is. What is your research question? What are you trying to get at? Are you trying to do some kind of prediction? Are you trying to assess a causal effect? Are you just trying to describe something in a kind of vague way? And depending on what it is that you're actually trying to do, the appropriate thing to do with this regression model, or introspect with it, or analyze it in some ways, is going to be different. So I like this paper here on the uses and abuses of regression models. And there's many papers like this one. This one is, I think, maybe just the most clear and most recent one. But there's tons of stuff in the literature, statisticians writing things like this, saying, hey, guys, what is your actual question? And the right way, people are, what's the right way to do this regression model? What's the right test? What's the right whatever? And it's like, it depends. So that's why you need to actually understand what it is that you're trying to do. And these guys say, generally speaking, there's 3 distinct types: descriptive, predictive, or causal. So that's partly why I have it laid out like this. And we'll see as we go through this portion where we're talking about regression, how those different use cases change what you're going to do with this and how you interpret the results that you get. So just keep that in mind. Okay, so why do we need methods, some kind of specialized methods for regression? Because you might be thinking, if a conditional mean is just an average within subgroups, why can't I just use the subgroup means? So here, let's say I have a covariate x and my outcome y. If these are my data, then so for each group of x, so here let's say x1, 2, 3, 4, can't I just take the sample average of my values in the data for each of those groups? So here I've marked that with that pink line. And here I'm showing you what that would look like if I wrote it out, or like try to notate it mathematically. So my conditional mean at a value x, so for example, 1, 2, 3, or 4, would be however many data points I have where x took that value, and then what 1 over that, so that's the n there, and then I'm adding up all the y values for the data where x took that particular value. So this notation just means take the mean of these 3 points, and that's the value at x equals 4. Take the mean of these points, and that's the value at x equals 3, and so on and so forth. Or if you prefer code, you take your data and you group by the value of x, and then you summarize, and you get mu is equal to mean of y. So this is the mean of y within each of those groups. Okay, so why not just do that? That's pretty straightforward. We don't really need anything more, right? And that's actually, if you thought of that, that's actually a really great intuition and a really great way to do things that is, in fact, in some senses, theoretically ideal. But it has some major practical problems. And the first of those is, okay, well, what if x is continuous? If x is continuous, then at every value of x, it'll look something more like this, right? At every value of x, we either have no observations, or for almost all values of x, we have no observations. And then for some values, we just have a single observation. So there's really nothing there to average over. And so if you want to apply this idea, you can think, well, maybe what I'll do is I'll just bin, right? I'll say like for x between 0 and 10, and then 10 and 20, and so on and so forth. So I'll bin them together, and then I'll take subgroup averages. But then you have the problem of, okay, how big do I make the bins? And you get into a lot of kind of practical issues there and ad hoc choices that you have to make. So similarly, even if you have a discrete covariate like this, if you have a lot of buckets or a lot of different values, like here it's just 4, but if I had 10, 20, 30, then you're going to end up with not very many people in each of those buckets. And as we've seen from previous lectures, if you're taking a sample mean of a small number of data points, there's going to be a lot of variance. So your estimate of the mean will be very bad. There's going to be, if you were to redo the experiment, you would get probably a vastly different estimate. And so that's not great. Furthermore, all of this gets worse if you have many covariates. So let's say you have 10 data points and a single binary covariate. So maybe you have like 5 and 5 in each group. Cool. Now imagine you have 2 binary covariates. So you have and each so now you have a total of 4 buckets, and you're splitting up those same 10 people into 4 buckets. So maybe you have 3, 3, 2, and 2. Now let's say you add another binary covariate. So now you have 2 times 2 times 2, that's 8 buckets and 10 people. Now you're going to get about 1 or 2 people in each bucket. So as you add covariates, as you add descriptors of these people, you're actually just making finer and finer buckets in which to put people in, which means there's going to be fewer people in each of them. And this, of course, happens with discrete covariates, but in a theoretical sense, also happens with continuous covariates. Everything gets kind of harder if you're trying to define like local averages. There's going to be fewer and fewer people in each neighborhood if you have more directions to kind of go in. So that's not good. So for these reasons, we need something else. Besides just looking at averages in subgroups, we need to be a little bit more sophisticated about how we do things.